Today we'd like to talk about what is the difference between DC and AC in the context of electric current. Well, DC stands for direct current and AC stands for alternating current. But what I really want to do is have you understand what the difference between the two really are. Why do we have two different kinds of electricity? There must be some pro and con of each side. So we want to talk about the pros and cons, what the similarities and differences are, how they're generated, and then generally why do we have two sort of different kinds of electricity. So DC stands for direct current. And so I have a very simple little diagram of direct current up here on the board. So this is a very simple circuit with a single voltage source and a single resistor and a single current. Now, before we can do anything, I need to remind you that when I talk about the voltage in a circuit, what it means is how much push is the generator pushing, for lack of a better word, on the electrons in the wire to get them to flow around the wire. So the voltage is simply the push, right? Now, the electrons which are actually flowing is called the electric current. So the voltage is the push, but what's actually moving is the electric current, the electrons moving around the circuit. And when they move around the circuit like this, they encounter resistances, which kind of slow down or impede the flow of electric current. Everything in real life, except for superconductors, which are a different animal, have real-life resistances associated with them. So any wire you have, circuit components, they all have resistances. So we have this voltage source, which is pushing the electric current out, which we call I, and then that flows through resistances. This could be a light bulb, this could be a wiring in a home, anything like this. And then it makes a closed loop back with the voltage source. Now, I want to say for a second that in electric circuits, the electrons in the wire are the free electrons in the metal, and that is what's actually moving. The electrons hop from atom to atom and make their way all the way around to the other side of the circuit. So the electrons are actually moving. They would come out of this negative side and they would go around this way. But in electrical engineering, we actually, instead of talking about negative electrons coming out of this terminal, we talk about the opposite current, which is like a fictitious positive current going the other direction. Mathematically, the two are exactly the same thing. So when you see diagrams in engineering, you'll see positive current flow as if positive charges are moving this way, when in reality, we know that negative charges are flowing the other way. So mathematically, they mean the same thing. Positive charges going one way or oppositely charged electrons going the opposite way, they yield mathematically the same calculations. So this is the positive fictitious current that we have going around this direction. So in direct current, what you need to realize is that the current is just a constant value flowing out of one terminal, going all the way around and circling back to the other side. It's direct because it basically doesn't change. It should be called unchanging current. That's what it really should be called instead of direct current, okay? We're going to see in a second that alternating current is changing all the time. It's flipping back and forth all the time, over and over and over again, but it's a little too fast for our eyes to see it when you look at light bulbs and things like that. But the light bulbs are actually flickering very fast with alternating current, okay? So we have this voltage source driving this electric current through this resistance. Now I put a resistor here to have something in the diagram, but just know that in real life, you may not only have resistance here, you might have capacitors here. The circuit symbol would be these little open plates right here. Or you might have inductances, right? Which we have, which we label L for inductance. So an inductor is just a coil of wire, and a capacitor is two parallel plates with a gap. Now, I'm not going to get into all of that now, but just suffice to say that these are very useful circuit components. There are also other components. Transistors are used in computers and other antennas and transmission lines to broadcast AM and FM frequencies. They're also used in computers for digital logic and things like that. So computers, transistors, diodes, transformers, there are many other circuit components. But to make it simple, let's just talk about a resistance, which is in our house. Maybe it's a light bulb or something like this. Now, in a direct current, what generates the voltage source? The most common thing is a battery. Any common battery you see around the house, from the very small ones that we have in little remote controls, all the way up to very large batteries that you might see in either in a regular car, a 12-volt battery, or a very high voltage battery in an electric vehicle. those always produce direct current. So when you have a battery and you connect it in a circuit, the electricity goes out of one terminal back to the other terminal, and it never switches direction, and it never changes in amplitude or intensity or anything like that. It's just a constant direct connection of current from one side to the other. So we use commonly direct current with batteries, and we use direct current is involved in solar panels. Those are the two most common situations when we have a need for direct current. In a solar panel, you have the photons coming in from the sun, and they strike a semiconductor panel, and the photons from the sun physically knock loose, for lack of a better word, one of the electrons in the solar panel, which then gets freed up because of the photon hit it. It gets freed up, and then it flows out to charge a battery or into a load of some kind to power it. So that's a direct current kind of deal as well. Obviously, there are many uses for solar panels and batteries, and so we'll talk about those in a little bit. But those are the main times you're going to encounter direct current. For almost every other use in our daily life, we use alternating current. All of the electricity in your house is alternating current coming out of the walls. All of your appliances plugged in, they're using alternating current. Even when you turn on a light bulb, it's using alternating current. And I'm going to talk about why we have alternating current and what alternating current is. So here is a circuit diagram for alternating current. Notice it's exactly the same thing, except I've replaced this, instead of what we had before with the plus minus, I've replaced it with a squiggly line. Now this is supposed to represent a sine wave or a cosine wave. You might remember from math class is that squiggly wave that goes up and down and up again. So that's what the voltage looks like. It's a sine wave or a cosine wave. They have the same shape. So whatever you want to say, sine or cosine. That is the shape of the voltage and the current in an alternating current circuit. Now I've drawn the current as a single arrow going this way, but that's a little bit of a misnomer. This is kind of a reference direction for the direction of the current, but really the current sometimes flows this way, but then it stops and it reverses direction, and then it flows the other way. And it flips back and forth, so it goes out through the resistor, and then it'll stop and it'll turn around and go back and back and back and back over and over again at what we call a steady frequency. So to visualize that, I have this silly little thing I put together. These are just some magnets to stick to the board. And here are my electrons inside of a wire. And you can see the little dots there, right? What I'm saying is the circuit will start off with the electrons flowing one direction like this. But after some small period of time, the flow of electrons will stop and they'll reverse direction and they'll come back the other way. Again, they're still flowing in a circuit. They're still flowing through the source and through the load, but they'll reverse and they'll go the other direction. Then they'll stop again, and then they'll reverse and they'll go this way. So back and forth, over and over. You see, if you trace one of these electrons, all it's doing is reversing direction back and forth, back and forth, back and forth, but it's still traveling through this closed circuit here that we have on the board. So this is the reference direction, but just know that it's going back and forth over and over again at a certain frequency. So we have to use the word frequency. In the United States, it's 60 cycles per second, which we use the unit of hertz. 60 cycles per second just means that that voltage oscillates back and forth 60 times every second. So if instead of a resistor, you put a light bulb here, if you put the light bulb in this circuit, the current is flowing around through the light bulb and it never changes. So you'll see the light bulb lit up, and it will never flicker. But if you put a light bulb in this circuit, if you had bionic eyes and could slow down time, you would see the light bulb get brighter and dimmer, brighter and dimmer, brighter and dimmer, brighter and dimmer, because the current is getting bigger, 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 then it turns around, then it goes the other way. It's getting bigger and smaller as it oscillates back and forth, and so the light would be getting brighter and dimmer very, very fast. You can't see it with your eyes, but with a high-speed camera, you can absolutely see incandescent light bulbs get brighter and dimmer over and over again. So let's zoom in on this voltage source here, and we'll talk about after that, why do we have two different kinds of current in the first place? What we're trying to say is if you were to graph this thing over time, so if you had time, and over here you have the voltage you were graphing, what this graph of the voltage would look like that sine wave that you learned about way back in algebra. Now I'm only drawing one cycle of it. You see it goes up and then back to where it starts, right? But it goes over and over and over and over and over again, never stops, right? So what this means is that when time starts, the voltage is positive and getting bigger. right? So then that means it would be plus minus and it would be getting bigger. And so therefore the current would be getting bigger as well. More electrons flowing per second, for lack of a better word, in this direction. As the voltage gets to a maximum, the light bulb would be the maximum brightness if this were a light bulb. But then the current begins to get small, the voltage begins to get smaller, which in turn drives the current smaller. Remember, the voltage is the push, and the current is how many electrons are flowing per second as a result of the push. So as the voltage begins to go down right here, then the current also goes down, the light bulb gets dimmer. But what happens when you cross here? This means that we've now reversed direction. Instead of the current flowing this way, then everything is stopped, and then the current begins to flow the other way, like this arrow, through the light bulb in the reverse direction. And it's going to be getting bigger and bigger and bigger in the negative sense. Just like with this, whenever we started, we did one direction, then it reversed and it went the other direction. And it gets bigger and bigger in the reverse direction, getting to maximum brightness right here, and then getting smaller and smaller again. Then it flips around the other way. And it does this every cycle. This is one complete cycle. It does it 60 times every second. So that's way faster than I can clap. You will not see it, but that is how it is done. All right, that's the difference in a nutshell. So that is the punchline. The difference between direct current and alternating current is direct current comes from batteries or solar panels. It generates a voltage and in turn a current flow which does not change, and it's fixed over time. It doesn't oscillate or flicker at all, right? That's what comes out of batteries. An alternating current circuit, which is what we use in all of our households and in all of our appliances, has a voltage that oscillates in the United States 60 times per second, but in other countries it's at slightly different frequencies. And in those situations, the voltage goes up and down, and so the resulting current also goes up and down 60 times per second. All right, so the question that we have here is what are these voltages? So in the DC system, the small batteries that you might get out of a drawer might be 1.5 volts. There's a 9-volt battery, and in cars there's a very large 12-volt battery there, and so different range of voltages here. What kind of voltages do you typically see in alternating current? Well, in the United States, again, it's different around the world, but the voltage here is typically very close to 120 volts. Now, where do you measure the voltage is kind of a little bit weird, because you think that you would measure the voltage to be the maximum, and so the maximum on this side, but actually we pick an intermediate value. It's called the root mean square value, because since this thing is oscillating over a cycle, you got to pick a good average value there. And so instead of picking the top or the bottom, we calculate it. I don't want to get into the details here, but we calculate the best average value to represent for power calculations of power circuits would be 120 volts. It's a little bit down lower than the peak there, and so that's the value that we use. We learn how to calculate that when you get into more detailed circuit analysis, okay? All right, so here, let's turn our attention to why do we have AC? We have DC current, batteries, and solar panels. Why do we even have AC? And what are the pros and cons? I should go back and say that way back in history, there were some proponents that were advocating that all of our electrical system would use direct current, the most famous of which is Thomas Edison. He thought that we should have direct current power transmission from the power plant to everybody's house. Obviously, you've heard of Thomas Edison, right? But the advocate for alternating current was Nikola Tesla. Now, there were others on both sides, of course. These are two obviously very famous scientists, and who actually won out for the transmission of power was alternating current. We're going to learn in just a second that alternating current turns out to be much more efficient to transmit over long distances. And so since we have a central power station generating either a nuclear power plant or a coal power plant or something like this, it's much more efficient to transmit it in alternating current form around the country there. But for solar panels on roofs, then it's much more efficient to just use the direct current, because the solar panels just generate direct current electricity and voltage and current directly out of the solar panel itself, okay? All right, so why do we have AC power anyway? The biggest use of AC power, as we mentioned, all of the electricity that comes out of the walls are oscillating at 60 times a second in the United States and other frequencies around the world. But the main reason that we have it, other than its efficiency, it's more efficient to transmit it. I'm going to talk about why in a minute. The other reason we have it is because generators that generate large amounts of electricity naturally generate alternating current. right? This is something I didn't learn till much later, and it makes a lot of sense. The reason why AC is so useful, other than the transmission efficiency, is because the coal power plants, the nuclear power plants, they all generate electricity by turning a coil of wire inside of a magnetic field. So if you have a coal power plant, what's really happening is you have a coal that you burn and it heats up water, which makes steam, and the steam turns a generator. And what that means is you have magnets and you have a coil of wire, and turning that coil of wire in a magnetic field generates electricity. I have pictures I'll show you in just a second. And the act of turning a wire in a magnetic field naturally generates a sinusoidal sine or cosine wave. And so it naturally is easier just to transmit that than to change it into direct current. And also it's more efficient as well. For DC, if it's batteries or solar panel, then it makes a little more sense for that. So let's talk a little bit about how these things are generated. What's the general idea behind that, right? So it looks complicated here, but it's very easy to understand. So here I have a very simple cartoon of an AC generator. Here is a magnet. This is the north pole of some magnet, and this is the south pole of some other magnet. Now, of course, the magnet has a back end I haven't drawn here, but just focus on what we have in the center. We have a magnetic field which then comes out of the north terminal and hits the southern terminal of this one. And the magnetic field, we usually use the letter B with an arrow on top to denote the magnetic field there. These lines represent the magnetic field going from one magnet to another. The magnets are not moving, the magnets are not changing. It's just like an invisible magnetic field between two bar magnets. Think of it like that. Now inside of this field, we put a loop of wire. Notice the wire is open over here. It's not connected, but it forms a closed loop here. And then what you do is you just rotate this loop of wire. Now you can amplify the effect by making more turns in this loop of wire. I've drawn one turn, but you might put 1,000 turns on here to amplify the effect. But basically, when you turn this thing, it turns out, no pun intended, that a voltage is generated across the terminals here, which is proportional to how much of this magnetic field cuts through and changes with time, cutting through this loop of wire, cutting through the cross-sectional area. So it's not generating voltage based on how much field is flowing through the loop. It's generating a voltage based on how much magnetic field lines are changing that are cutting through there. Changing is a better word. So don't think how much magnetic field is going through there. Think how much is the magnetic field changing, right? So I have the magnetic field, the loop of wire drawn like this in this diagram here. And then later on, I have it drawn like this where it's perpendicular to the magnetic field. So you see right here, if you consider this loop of wire rotated a little bit, the magnetic field is coming from this direction, going through the loop, and then exiting here. So we have a large magnetic field going through the loop in this case. Here I've drawn the loop flat. So the magnetic field is not intersecting at all with the loop. So we say in this case that there's not very much magnetic flux. The word flux means magnetic field lines. There's not very much flux intersecting the loop because the loop is parallel to the magnetic field. But here there's a lot of magnetic flux intersecting with the loop because it's literally broadside to the magnetic field right here. So the voltage that is generated when this thing turns is proportional to how much flux is changing through time that's cutting through the loop. One more time, it's proportional, the voltage you get is proportional in the generator to how much magnetic field is changing over time, right? So when you look here, there's a lot of flux going through the loop, but as the thing turns, notice it's turning like this, it's rotating like this. If it turns a little bit, notice that it's still almost completely broadside to the magnetic field. So here there's a lot of flux, and if you rotate a little bit, there's still almost exactly the same amount of flux going through this loop because it hasn't really moved very much of an angle right here. So here, because there's not very much flux changing that is cut through this loop, we say that in this case, there's going to be less voltage generated, okay? But in this case, when we're parallel to it, there's no flux at all cutting through my loop because it's parallel like this. But if I rotate this just a little bit, notice it goes from 0 flux to non-zero flux, even if I move it just a little bit. So even though there's not much flux here, it's the change in the flux that's being cut. And when you go from nothing to something, you get a bigger change than what you have down here. So you generate more voltage in this case. So you have a changing voltage that is happening. Sometimes when the current loop is oriented like this, you get less voltage. As it rotates, then you get perpendicular, and then you're getting less voltage. So more voltage, less voltage, more and less. And then as it rotates around, it flips in direction, and you get the same thing, more and less, more and less. And so from that, what you end up getting is a voltage graph as a function of time, and sometimes you're going to have less voltage and sometimes you're going to have more. Then sometimes you're going to have more voltage in the other direction, and then you're going to get back to 0. So this is positive when the loop is oriented one way, and then negative when the loop flips around physically and rotates the other direction. So the reason why AC current is so common, other than the fact that it's more efficient to transport, is because all of these generators, even nuclear power plants, the way a nuclear power plant works, yes, there's a nuclear fuel making some heat, but all it does is heat up some water, which turns into steam, and the steam turns a generator. So we're still turning generators, which are coils of wire in a magnetic field to generate all of our electricity, even if it's a nuclear power plant or a gas power plant or a coal power plant. Any kind of large-scale power generation simply turns a coil of wire in a magnetic field, and it generates a sinusoidal voltage, because this is the kind of shape you get when you take a circular, when you turn things through a circle, basically. And when you look at how much is cut through there, that's the kind of shape of voltage that you're going to get over time as it makes a full revolution around. And if you turn this thing 60 times a second, you're going to get 60 times a second down there. Now, in reality, we don't turn generators at 60 times a second. The voltage is generated at much, much higher voltages in power plants and then transmitted over much, much, much higher voltages, thousands of volts, kilovolts, across the country until it gets to a city, and then there's a substation, and then that AC voltage is reduced in voltage from thousands of volts to lower thousands of volts, right? Instead of 100,000 volts, maybe 10,000 volts. And then when it gets into the neighborhood and into the home, it is stepped down again using transformers, I'll talk about in a second, down to the 120 volts, the safer voltages that we have inside of our house. So another reason why AC is so common is because we can turn the voltage very, very high, and we can transport the power without losing any electricity in the process, or losing less of it due to heating up the wires, the transmission wires. And then when we get to the neighborhood, we turn that voltage back down using transformers into a safer voltage, which can be used inside of the home. All right, so I want to talk a little bit about that process over here. All right, let's say that you have some voltage generated at a power plant. And so I'll put a big circle around this because it's a source, but it's a generator at a power plant. And then you have some long transmission line which has resistance in it. It also has capacitance and inductance, but we're going to focus on the line resistance. So I'm going to call this the line resistance. And then once it gets to some houses or a substation and then some houses, you have some houses over here. And so it could be like, 50 houses or 100 houses or 1,000 houses or whatever. But it's going from a power plant through a transmission line into a neighborhood, into a bunch of houses, and then back to the power plant again. All right, so there's some very simple equations that govern all this stuff. Power in electric circuits is always equal to whatever current you have flowing in the wire multiplied by the voltage that is pushing. Remember, the voltage is the push, and the current is how many electrons per second are coming out as a result of the push, right? It's just like pressure in a water hose, that's the voltage, and the water flow is the current. It's exactly the same situation. Very, very similar analogy, okay? But the power, which is how much work you can do to turn a motor or whatever and to make something happen, the power is just how much current is flowing multiplied by the voltage. And of course, there's some current here, but remember, this is AC, so it's all oscillating. It's not just flowing one direction, it's back and forth, the back and forth, the back and forth, just like we said before. Now this power here, this power is basically the power demands, so I'll put power, requirements of whatever neighborhood. You might need a megawatt or a few 100,000 watts of power or something for like a whole neighborhood or something down here, but this is the power P that I'm talking about right here. So that's the power P right here. But what happens if we solve this equation for the current, right? If we solve this equation for the current, we divide by the voltage and we get the power requirements divided by the voltage. So what I'm trying to say is, if you need a fixed amount of power in a neighborhood, you hold this thing constant. If you increase the voltage higher, then you need a smaller current to supply that power. So we want to run the voltage on the lines as high as possible, because for a fixed amount of power the neighborhood needs, if I run at a much, much higher voltage, I don't need very much current to do it, right? Why do I care about that? Because we have this resistance in the line right here, and the current is flowing through the line on the way to the houses, right? So you have something called line losses, right? So you have a power loss associated with the power line itself, and that is given, and you can learn where this comes from in electrical engineering, I squared times R. So the power loss in the transmission line itself is related to the resistance multiplied by the current, but not just the current, it's the current squared. So however many amps of current squared, that and then multiplied by the resistance, that is how much I'm going to lose in transmission losses of energy loss in the wire. So if I run at a very high voltage, I don't need to put much current in that wire. And then because this is lower and it's I squared, it's very, very dependent on the current. Then my losses are low. So here is why we need AC. This is why we settled on AC instead of DC. We went with Tesla instead of Edison. Because if we run the transmission lines at a high voltage, then we don't need to put as much current flowing in the wires. And because the losses in the wires over hundreds or thousands of kilometers is proportional to the current squared times the resistance in the line, then by reducing the current, then we don't have very many line losses. So then we can transmit over very large distances without the power lines heating up so much and without losing so much electricity. If we use direct current, we would lose tons of energy just heating the wire up. So from A to B, we would lose tons of energy before we could even use it, because the wire would be heating up more if we went in that direction. All right. Finally, the last little piece of it I'll leave you for, or I'll leave with you, is we said that when we get from the power plants a very high voltage, when we get into the neighborhood or into the substation, we step it down from a high voltage to a lower, safer voltage. For instance, in your house is 120 volts in the United States. How do we do that? We have something called a transformer. And you may have heard, oh, the transformer blew, so the power company has to go fix it or whatever. A transformer is an iron core or some kind of magnetic core with a coil of wire wound on one side and then a coil of wire wound on the other side. And the number of turns on this side is different than the number of turns of wire on the other side. So it's literally, pretend this is a piece of iron. It's literally a coil of wire wound around it and then another coil of wire around wound around the other side. And it turns out that when you have alternating current on this side going back and forth, and then you wind another coil of wire on the same magnetic core, then the voltage can be transformed either higher or lower depending on how you choose these turns. If you have a higher number of turns on one side or a lower number of turns on the other side, you can control if the voltage goes up or down across the transformer. That's why it's called a transformer. It transforms the voltage either higher or lower. In this case, we have a high voltage generated at the power plant. We transmit everything across the power lines very efficiently with very low loss. Then when we get to the substation, we step it down from maybe 100,000 volts to maybe 10,000 volts using transformers. And then when we get into the neighborhood and the houses, it's further stepped down into the 120 volts that we have and that we can use safely. So that was an overview of what DC is. DC is electricity where electrons are flowing in one direction only, no oscillations, no bigger and smaller, just one way, and that's it. Alternating current is when the electricity literally switches directions at a frequency. In our country, it's 60 times a second. In other countries, it's 50 times a second in other frequencies. And the reason we do it is because generators generate electricity, at least large-scale generators, in AC, and it's easier to transport it without losses to the destination. But if you're working with solar panels, like solar panels, solar farms are a big thing nowadays, then DC makes a lot more sense. Also, you might say, well, DC is so crazy, why would we ever use it? Well, there's sometimes when you have to use DC. For instance, if you're building a space probe and it's going out to the outer edge of the solar system, it's way better to have a solar panel. It depends on how far you go, actually, but around Mars, Mars is still close enough to the sun where we can use solar panels. Beyond Mars, maybe we can't use solar panels. But in Earth orbit, we use solar panels and batteries all the time because it's easier than having a generator turning, which is a lot of moving parts, because they're simpler and they don't break down as much. Right? Also, small devices, remote controls, small electronics that just need a tiny little power source. You have that battery. We didn't talk at all about what's inside the battery, but in general, there's a chemical reaction in there, and the chemical reaction is transferring electrons from one side of the reaction to the other, and those electrons, when they transfer, they go through the circuit to get to the other side. When you deplete the chemicals that are inside the battery, then the battery doesn't work anymore. So it's a one-time thing unless you can charge it back up again. But once it's done because the chemical energy inside of it is depleted, right? But there's less moving parts in batteries. So they have different uses, and obviously AC and DC are all here to stay. I hope you learned something. I hope you enjoyed it. Please follow me on to the next one. Learn anything at mathandscience.com.